A recent research paper suggests that large language models, LLMs, might not be as dependable as we hoped, especially when the simplest changes to math problems cause their accuracy to plummet. We're talking about a whopping 30% drop in performance, enough to make big industries think twice before rolling these models out in critical areas like finance and business. Let's dive into the details and see why this is a wake-up call for the entire AI community. The paper introduces the Putnam-Axom Original Benchmark, featuring 236 math problems from the William Lowell Putnam competition. To guard against test leakage, where models might have seen these problems online during training, the researchers built a Putnam-Axom validation benchmark. They slightly altered 52 of the original problems, changing just variables or constants, to create entirely fresh challenges. Despite these being minor tweaks, the best-performing model, OpenAI's 0-1 preview, saw its accuracy drop by nearly 30% on these new variations. This suggests models are good at recalling problems they've already seen, but may struggle when faced with genuinely new examples. Two main alterations were tested. Variable change. Only the variable names changed, so the math remained identical in structure. Constant change. The numeric values changed, forcing the model to recalculate rather than rely on memorized numbers. These modifications are small, yet they're revealing a big flaw. The models often falter when the exact questions aren't identical to what they've previously learned. A key chart in the paper shows a sharp decline in performance for nearly all tested models once the problems were varied. For instance, OpenAI's 0-1 preview might score around 50% on original questions, but tumble to about 35% or less when even basic elements are changed. Researchers see this as a serious reliability issue. If the model can't maintain accuracy on slightly tweaked problems, how can we trust it in high-stakes applications? One likely culprit is overfitting. When an LLM is trained extensively on a specific dataset, like popular math benchmarks, it may learn those examples too well. As a result, when it encounters real-world questions or even just minor variations, it can't generalize effectively. Smaller models in particular are at risk of overfitting, performing impressively on rehearsed test problems but stumbling on new ones. Another issue the paper highlights is data contamination. Sometimes parts of the test questions accidentally end up in the model's training data. This inflates a model's apparent performance. Once the question is modified, the model loses this unfair advantage and its accuracy plunges. Because LLMs are trained on massive internet datasets, it's tough to ensure none of the benchmark content made it into the training set. For GPT-based models, like GPT-40 mentioned in the paper, there were additional problems: logical leaps and incoherent reasoning. The system occasionally claimed to have the correct solution with no proof or justification. This indicates the model might be rushing to match a memorized final answer, rather than offering genuine, step-by-step logical reasoning. Despite these shortcomings, OpenAI's 0-1 preview still topped the charts on the new Putnam-Axom benchmark, about 42% accuracy. However, many of its answers lacked rigorous explanations. Researchers noted it often made leaps in logic without fully justifying each step. While it shows potential, it's clear there's room for improvement before we can fully trust it for advanced mathematical tasks. Interestingly, Apple's earlier research on math benchmarks highlighted a similar trend. Even modest tweaks, like adding an extra clause or changing symbols, led to alarming accuracy drops. They concluded that many LLMs aren't truly reasoning through problems. They're simply reproducing patterns they've seen before. Once those patterns shift, the models struggle. Overall, this new Putnam-Axom study, and similar ones, underscore the importance of creating robust benchmarks that genuinely test a model's reasoning. Minor alterations to variables or constants shouldn't cause catastrophic drops in performance, while newer or more specialized models like improved 0-1 or 0-3 versions may do better. This is a reminder to stay vigilant. If we want AI capable of reliable, broad-scale deployment, we must ensure it can handle novel variations, not just regurgitate known problems. The future of AI depends on developing models that can truly think, not just memorize.